Welcome to True Projects. In this video, we are going to explain about the project that is TLEABL-CNN Brain and Alzheimer's Disease Detection using Attention-Based Explainable Deep Learning and SMORT using Imbalanced MRI dataset. So before getting into the execution, first let us understand what is this project about. So, Alzheimer's disease. It is one of the leading causes of dementia, which gradually damages memory, thinking ability, and also everyday functioning in older adults. It is not just about memory loss. Over time, it impacts the brain's normal psychological process, making daily life very difficult for patients. On the other hand, brain tumors such as gliomas, meningiomas, and pituitary tumors are abnormal growths inside the brain that alter its structure and activity. These conditions are extremely serious as they can disrupt important brain functions and even become life threatening. So, here, to diagnose such conditions, doctors commonly rely on magnetic resonance imaging as it gives detailed and high quality images of the brain. However, reading and interpreting MRI scans is time consuming. That requires highly trained radiologists. Even then, differences in expertise and experience among specialists can sometimes lead to misdiagnosis. This makes early detection difficult, delaying treatment and reducing the chances of effective medical intervention. So, artificial intelligence techniques and deep learning methods have emerged as promising tool to support medical imaging. These methods they can process thousands of MRI scans quickly, reducing the manual workload of doctors. However, the doctors, that is, they are not free from challenges. One major difficulty in diagnosing AD, that is Alzheimer's disease and brain tumors, is that the differences in MRI images can be very subtle and difficult to compare. Models trained on such data may fail to generalize well, especially when the data is imbalanced, with some disease categories having very few samples. And moreover, deep learning models often tend to overfit when trained on small data sets, meaning they perform well on training data, that is, training images, but poorly on unseen images. And the other issue is the black box. That is the issue with the AI models, they act like black box. They give predictions without explaining why or how they arrived at those results. For medical professionals, this lack of transparency reduces the trust, since doctors need not only accurate results but also interpretable insights to support clinical decision making. These limitations highlight the urgent need for a reliable, efficient, and interpretable system for early diagnosis of a neurological diseases. So to address these challenges, this project it introduces a new lightweight framework called TLEABL-CNN, that is Transfer Learning Efficient Net with Attention Block CNN. So this is the proposed model. The strength of this system lies in combining transfer learning with efficient net as base model, which already has a strong pre-trained features with a squeeze attention block in it to focus on the most important parts of the MRI scans by emphasizing the most relevant regions. So the system ensures that subtle differences in brain structure are captured more effectively than with the conventional models. And the architecture is designed to prevent overfitting and also improve generalization. So it incorporates several regularization techniques such as L2 regularization, batch normalization, and dropout. These help the model to learn more robust features without becoming too dependent on the training data. The use of global average pooling also reduces complexity while retaining essential spatial information. The final layer classifies MRI images into 7 categories, covering multiple types of brain diseases, including Alzheimer's and brain tumors. And one of the biggest issue with the medical image data sets is the class imbalance, where some disease categories are underrepresented compared to others. So to overcome with this, the system uses a technique called synthetic minority oversampling technique, that is SMOOT. It generates synthetic samples for the minority class, making sure that all classes are fairly represented during training. This allows the model to learn equally well across different disease types rather than being biased towards the majority class. So the benefit of this approach is twofold. It reduces the chance of misclassifying rare diseases and also it improves the overall accuracy of the model. Without balancing, the model might ignore minority classes, which is dangerous in medical applications. What's more, the model becomes more reliable and fair, ensuring that every disease type gets proper attention during the learning process. And an important highlight of this proposed system is to focus on the interpretability. The framework integrates gradient weighted class activation mapping, that is GradCam. This helps to visualize the regions of an MRI scan that influence the model decision. This is critical because it follows, that is, it allows doctors to see not just the prediction but also why behind it. For example, the heat map generated by GradCam shows which areas of the brain the model considered important for detecting Alzheimer's or a tumor. This transparency builds clinical trust. So, medical professionals can cross check the highlighted areas where their expertise to validate the model's predictions rather than being a black box. The system becomes a decision support tool providing both the results and insights. So, this makes it more acceptable and also useful in healthcare environments. Moving on, as an extension, the system incorporates additional models to further boost the accuracy. So, for the classification, here we are incorporating exception and an ensemble voting classifier. These models helps in refining the classification performance by leveraging different decision making approaches. Ensemble learning in particular combines multiple models, reducing errors and ensuring stronger overall predictions compared to the use that is using a single model. And beyond classification, the framework has been extended to detection by integrating YOLO based models. So here we are incorporating You Only Look Once model. It is a well known for its ability to perform object detection in real time. This setup, YOLO models are trained to not just classify but also to localize abnormalities by drawing bounding box around the suspicious regions in the MRI images. This step takes the system beyond just classification and makes it capable of actual medical image detection. And moreover, here we have added a user-friendly front-end interface. So to make the system practicable and user-friendly, a web interface has been built using the Flash framework. This interface comes with a user authentication, ensuring that only authorized users, such as medical professionals or registered patients, can access it. That is, the users, whoever will be registered, only they will be able to log into the system and do the prediction. The backend process, that is, the backend then process the uploaded images using the trained classification and detection models. So when user gets registered, he will be able to do prediction. So for that, he will be giving the input images that will be pre-processed at the backend. The output includes both the predicted disease class and also the MRI scan with the bounding boxes around abnormalities, along with the confidence scores. This creates a complete pipeline that starts from uploading an image and ends with a clear interpretable results. Moving on to the implementation of the project. To implement this project, we have followed the steps which are mentioned in this flow of work. So let's understand them. First, we have imported all the necessary libraries that support data handling, image processing, deep learning, and visualization. Libraries like NumPy, Pandas, Matplotlib are used for data manipulation and visualization, while Torch and TensorFlow frameworks and Torch Vision are used for model building and augmentation. OpenCV and PIL are used for image pre-processing tasks. Then comes data preparation. So for this, dataset of brain tumor and Alzheimer's disease are collected and merged into a single unified dataset. The combined dataset is divided into 7 classes, representing different brain conditions. For the classification, images are stored along with their corresponding class labels. For the YOLO detection branch, bounding box annotations in the YOLO format, that is TXT files, are prepared to mark abnormal regions in the MRA scans. After annotation, the dataset is split into training and validation to ensure proper evaluation of the models. Then we have done some visualization. So once the dataset is ready, visualization is performed to better understand the data distribution, and a bar graph is created to display the number of samples in each class, which also highlights class imbalance. Additionally, sample labeled images are shown to confirm that annotations and pre-processing have been applied correctly before training. Then comes pre-processing. So here in the stage, image pre-processing is crucial step to ensure consistency. So all images are resized, normalized and augmented to improve model generalization. So torch vision has been used that is used for augmentation such as flipping, rotation and cropping. Since medical datasets often suffer from imbalance, synthetic minority oversampling technique is applied to the classification dataset. This ensures that all classes, especially minority categories, are fairly represented. And for the YOLO branch, a data.yml file is created containing paths to the images and class names. Finally, two parallel datasets are maintained. One for the classification, which contains images along with the labels, and another for detection, that is, images with the bounding box annotations. Then comes model training. So, here in this stage, we will be training all the machine learning models and deep learning models for the classification and for detection, that is, for localization of abnormalities. Different versions of the YOLO are trained. These models are capable of detecting both where the abnormality is and what the type of it belongs to. Then comes model evaluation. So here at this stage, all the models that are built will be evaluated using accuracy, precision, recall, and FN score, confusion matrix, and ROC AUC. And we evaluate detection models using these metrics. And we will be saving the best performing model for the future use. Coming to inference pipeline. So here, the inference stage, it defines how the system processes a new MRI image. The user uploads an MRI scan, so the trained YOLO model highlights the abnormal regions with a bounding box, while classifying model predicts, that is, while classification model predicts the disease type or the class along with the confidence scores. Coming to the front end, to make the system usable, a Flash-based front end is developed. It includes user registration and login functionality using an SQLite database for secure authentication. This interface is simple and user-friendly, allowing medical experts, that is users, to access the system. And here at this stage, user he will be uploading MRI through a web interface that will be pre-processed to match the trained model's input requirements. And the trained classification and detection models are applied to generate predictions. Finally, the results are displayed on the front end, showing MRI scan with bounding boxes and the predicted disease class associated with the confidence scores. Moving on. So these are the algorithms used in this project. So these are the machine learning models used, and these are the deep learning models. This is the proposed model, and these are the extension models. So these models are used for classification. Now coming to detection, these are the models used for detection. These are the different versions of YOLO. And to implement this project, we need hardware and software requirements. In hardware, we need operating system of Windows, processor of 5 and above, RAM of 8 GB, and hard disk of 25 GB and above. Software requirements are application of Python, front-end framework of Flask, backend framework of Jupyter Notebook, database of SQLite 3, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. So this is the overview of the project. Now let's execute it. To execute, open the code folder that contains source code files. So let's open it. These are the source code files of this project. So let's see the dataset first. Open the dataset folder. So here we have two datasets, that is brain dataset and this Alzheimer's dataset. Let's open brain data. So open training folder. Here we have four types of brain tumors, that is glioma, meningioma, node tumor, and pituitary. So open glioma. Here we have images of the MRI dataset where the person has glioma. And here we have meningioma, brain tumor, and here with the node tumor, and here with the pituitary tumor. Now get back. Get back. Similarly, we will be having in the testing folder also. And let's open this one. Open train folder. So here we have for Alzheimer's disease. So here we have for AD. And here we have for control. And here we have for PD. Get back. Get back. So these both data sets are combined and stored in this folder. Here you can observe total we have 7 different classes. Now get back. And this is the model folder in which we have algorithm information that will be loaded into the project. during runtime of the application. And the next one we have is the static folder, in which we have CSS, JavaScript, and Bootstrap file, which are important for the visual appeal of this project. Then we have templates folder. This folder contains all the HTML pages used in this project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And then we have test cases that we will be using in the front end. And here in this folder, we have the dataset that is used. So here in the train folder, we have two subfolders. One is images and labels. In images, we will be having the images, and in labels folder, we will be having the locations of the tumor of these images. Let's open images folder. So these are the images using which we will be training YOLO models for detection. Now get back. And in this label folder, we have files containing annotations or labels for the objects in the corresponding images. So here each label file, it corresponds to an image file in the image folder. For example, this first file, it corresponds to this first image in which we will be having tumor locations. Accordingly, for second image, we will be having second label file. So for all the 1093 images, we have 1093 files, and these files, they follow the YOLO format. Now get back. So we will be having in validation also. Those we will be using for testing the model. Now get back. This is the app file. So this file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in HTML templates. These are the two Jupyter Notebook files which contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. And in this file, that is in this classification Jupyter source file, we will be writing the code for loading this dataset and for training the models for just classifying the tumor type. And coming here, we will be training all the models. I mean, we will be training YOLO models for doing detection. And this is the sign up file in which we will be, that is a database file in which database will be stored. So this is all about the code folder. Now let's execute. So copy the path of the code folder from the address bar of the file explorer. Type Ctrl C or just copy it. Now open Anaconda prompt. It is open. Now give the command cd, give the space, and paste the copied path. Now click on enter. Here, if you observe, current directory is changed to the code folder's path. Now compile app.py file. So give the command python space app.py and click on enter. This command will execute Python script and perform runtime check for syntax errors or logical issues. And after running the app.py file, Flask framework will host the application locally at the default address, which is the local host and the port, unless configured differently. So just wait for a while. It is being compiled. This is the address where application has been hosted. So this is the local host. This is the local host, and this 5000 is the port. Now copy this local link provided by the Flask framework and paste it into any web browser. I've copied the link. I prefer Google Chrome, so I will paste it in that. Paste the link here. Now click on enter. So this is the web page of the project, which is displayed in the browser, and this is developed using Flask framework. Now click on register. So you need to create an account. For creating an account, you need to fill in all these details. I have already created, so I'll directly log in. Click on login. Give your username and the password. Now click on sign in. So we are redirected to classification of this project, that is classification page of this project. So let's do classification. So click on try demo. Under prediction, click on classification. So click on try classification. Click on choose file to upload the images. So click on this choose file. Open test cases. So we're doing classification, open classification folder. So let's try with this one. Select this image, click on open. So this given image, click on classify image. So this image will be pre-processed at the backend. It will be fed to the trained model, and then trained model will be giving us the prediction. If you observe, we have predicted result as AD, that is Alzheimer's disease. So here, the predicted result shows the model has classified the given MRI image as Alzheimer's disease. So this is the image that we have given, and it is predicting it as Alzheimer's disease. And here the model provides confidence scores which indicates the probability of image belonging to each class. So here in this example, so here for this prediction, it is showing AD, that is Alzheimer's disease, to be 93.31%. That is the highest probability. Hence the final predicted result is this Alzheimer's disease. And here we have control, that is 6.29%. And here we have glioma, that is 0.25, which is very low confidence, almost negligible. Here, the model considered it might be normal, but with much lower confidence. So, highest confidence has the Alzheimer's disease. That is why the model is predicting this image to be Alzheimer's disease. And here, if you observe, we have GradCam image. So this is the GradCam image. This image highlights the regions of the MRI that the model considers most important for its prediction. Here, red and yellow region. So it is considering red and yellow areas to show high influence, indicating where the model focused to classify the tumor. It helps to validate the model and support medical interpretation. Now let's try with one more image. Click on try image, click on try classification, click on choose file, and get back. Open the folder, select any image of your choice. Now click on classify. And here we have prediction as control, which means there are no type of diseases to the person. And here we have 88.98% of confidence score for the control. So that is why the application is predicting the uploaded image to be controlled. And here this is the GradCam image, and 10.79% for Alzheimer's disease and 0.7, which is very negligible. Let's try with one more image. Click on try classification, click on choose file. Now get back, open this one, select this one. And here we got the prediction as glioma, which has 97.19% of confidence score. And this is the image we have uploaded, and this is a GradCam image. Now let's check with the other image. Get back, open this one, select this image. Now click on classify image. And here we got the prediction as meningioma brain tumor. Here you can observe this is the MRI image that we have uploaded, and here we have 99.86% of confidence score for meningioma and 0.13 for no tumor and control for 0.01. And this is the area where the application is focusing on to classify the image to be meningioma. Now click on try another image. Now let us upload image from no tumor. So select any image, click on classify. And here we got the prediction that it is no tumor. Yes, no tumor, and this is the GradCam image. Click on try another, click on choose file, get back, click on this. Now select any image. So here if you observe, we got prediction result to be PD, which is Parkinson's disease, that is a neurodegenerative disorder. And here we have 99.55% of confidence score for that. This is the uploaded one, and here is the GradCam image. Let's try with one more. Click on choose file. Get back. Now open this pituitary folder, select any image, click on classify image. Here if you observe, we have pituitary prediction with the 9.80 confidence score, and this is the image, and here we have GradCam image. So pituitary glioma, meningioma and no tumor refers to the brain tumor type, and control, Alzheimer's disease and Parkinson's disease are the brain's neurodegenerative disorders. So here if you observe, we have clubbed both the Alzheimer's disease and also the brain tumor detection, that is brain tumor classification. Now let's do detection. So click on detection, click on try detection, click on choose file, get back to detection folder, select this image and click on detect image. So here we got the detection. If you observe, we can see a blue color box is drawn around the image and predicted as AD, that is Alzheimer's disease, with the 0.92 detection score, that is confidence level, how accurate the detection is. Let's try with one more. Click on try detection, click on choose file. Now let us upload this one. And here we got the prediction as Alzheimer's disease. Let's check with some more. Click on try again, click on choose file. Now let's upload this one. So here if you observe, we can see a control detection which is drawn in a blue color bounding box with a 0.92 detection score, that is confidence level. Click on try detection. And now let's try with this one. And here we got the brain tumor detection and drawn in a green color bounding box. So this is the area where the person is affected with the meningioma brain tumor. Click on try another. Click on choose file. And now let us upload this one. So here person has no tumor. That is why it is detecting it as no tumor. Click on try detection, choose file, and let's upload this one and detect image. So here if you observe, we have detection of PD, that is Parkinson's disease. That is which is a neurodegenerative disorder it is. It is not the tumor, it is neurodegenerative disorder where he has problems with the nerves in the brain. And tumor is the cancerous cells that are present in the brain. So here the application is detecting both the tumors as well as neurodegenerative disorders that are Alzheimer's. Now let's try with some more. Click on choose file. Scroll down. Now let's try with this one and click on detect image. So here we got the detection as glioma. In this way you can do detection. So when we have uploaded images for classification, it was just telling which type of Alzheimer's the patient has or which type of tumor the patient has. In detection, it will highlight the area where, that is, it will draw a bounding box in the area where the tumor or the Alzheimer's area, that is abnormal region, is present in that brain tumor. Now let's check with the graphs. Click on graph. So here we have multiple images. So the first one we have is number of images per class. Here if you observe, on x-axis we have different classes that we have predicted, and on y-axis we have number of images. Here if you observe, AD and control are higher and this PD class is very low. So that is why we have used smooth technique. Now get back. And here we have confusion matrix. Open it. This is the confusion matrix. And here we have ROC curve graph. This is the ROC curve graph. Get back. And here, this is the model performance comparison graph. Here, if you observe, on x-axis, we have all the algorithms that we have trained, and on y-axis, we have accuracy score. And here we have all the algorithms, precision score, recall score, and FN score. So these are the evaluation metrics that are used to evaluate the models that we have trained. And here, in this page, we have model performance of section B. Let's open it. This is section A and this is section B. Let's open it. So this is for the scenario B. So, and this is for scenario C. This is for the scenario C. And here we have bubble chart. open it. So this is model performance bubble chart. Now close it. Similarly, we have for YOLO graphs also. So this is the YOLO graph of precision score. Here on x-axis we have all the models that we have trained, and on y-axis we have precision score. And here we have for recall score, and here we have for mean average precision. Now click on logout. In this way, just by uploading images to the application by using deep learning models and the YOLO model for detection, application will be correctly detecting and classifying whether the person has Alzheimer's disease or whether the person has brain tumor disease. So this is all about the project.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.